Hello. Perfect.
That's the problem with mutable interfaces.
Yeah, it's ridiculous. Okie dokie. So, last time, we were trying to look at functors, but I, in retrospect, thought I did a bad explanation of what that was. So, what we've done, we're gonna start from like kind of first principles, and I'm gonna give you some backstory. I've recently been researching my family history. I've been sitting on ancestry.com and I've like built this, like, I've been going through all these like records, you know, and I've built this like family tree, right? And this family tree is, it's effectively a tree. It's rooted in one node, which happens to be me. I'm 22. I have a mother and a father, and I know only about my mum's mum, and I only know about my dad's dad. And you'll see that, yeah, each family member has an age. They might have a mother that I know about, they might have a father that I know about, and I've defined this method on each family member called parents, right? And it goes through both my mother and father, and if they exist, puts it in the list, and if they don't exist, we don't put that in that list. And so for a little refresher, option is this data type where it's either none in this instance or it's some, right? It's a value that says it has two different variants. Yeah, it's effectively equivalent to a value that is not null or is null. It's like it's there or it's not there. So that's what option is, right? So I'm going to define two kind of functions for family members. This one says it's called get parent ages, and it goes through, it gets a family member, it goes to the parents, and it gets their ages, right? Everyone following so far? And then we've got another function called get mother's age, and it gets, if that family member has a mother, it gets their age. But if they don't have a mother, it doesn't return anything. It says none, right? So you can see here, get parents' age, goes through my parents' age, 55, 56. But if I get to try and get the parents' ages of my grandmother, can't find anything, so it goes empty list. Get mother's age, might be, you know, it's 55, but if I try and get the mother's age of my grandma, it says none. Couldn't find my grandmother. So we can kind of see that there's like this kind of common pattern where, you know, we're trying to get into some sort of thing. We're trying to go into a list and get an age here, and here we're trying to get into an option and we're trying to get an age here. There's something like there's some duplicated code here, right? And you know, we can pull these out into separate functions. This one takes a list of family member, it gets int out. This one and gets a list of integers out. This one takes a optional family member and gets an optional int out. You can kind of see what's going on here. It does effectively the same thing, you know. So we want to do something like this. We want to create some sort of function that for any type f, with some sort of like requirement of that f, an f of family member, I can get an f of age. So we have a list of family member and we can get a list of int, which is an age. We have an option of family member, we can get an option of int. And here we have some arbitrary f of a family member, gives some arbitrary f of an int. And just like how we use map here, and we use map here, we're going to use map here again. So we've made this generalized function that works across both those things. This has a name, right? Some people, they're like, okay, it's map, so it's called mappable, right? For various math reasons, we call them functors. And so a functor, if those are who are familiar with the last thing, this is our type class that we looked at last time. It's something, some functor f is a type that has this like thing defined against it, a map function that takes a excessive function and then gives you whatever the destination value of that excessive function is. So for example, here we've gone from an option of family member to an option of int. This map took family member to int. So we can actually expand this out, family member, oh shit, member, family member, right? For those who are unfamiliar with this like kind of shorthand syntax, a member to a family member, right? So it's taking family member to an age. So this successor function would be family member to age, and it would return an option of it, right? So remember from last time, we define our syntax for something that is for some f with some value inside of it. We define the syntax against it that recovers the functor instance and then calls map on that instance with that accessor function. Everyone following so far? This is kind of like what we looked at last time. We can go back and go over it if we've kind of forgotten. So let's do some instances for some things that we know how to do. Here is list. List is kind of takes a list and some mapping function and takes a list of A, mapping function, and gives us a list of B, right? And we can do that here as an example. List 1, 2, 3. We have a mapping function. Oh, sorry, I cannot see what this is actually. Map and mapper function. There we are. Oh, Jesus. And then we can change the type if we want to string like that. It's a list of string. So we've changed our list of ints to a list of string because we have a function that goes into string. Cool. Everyone fine? Sweet. So we don't want to re-implement map because this is the implementation. It's very scary. It's a lot of mutability. Oh, yuck. That's for lists. For options, it's kind of simple. No, simpler. Given some option and a mapping function, if the value exists, apply the function and wrap it up again. If the value doesn't exist, just say that it doesn't exist. Like you can't get the age of a family member that isn't around. So, if you had a non-existent family member, you now have a non-existent age. But if you have a family member, you now have an age, right? Some family member goes to a sum of age, right? So here we can use it. Now, here's our little function that we made, the one that we wanted to do before. Now we have this like get age function, and it works across two different types. It works across families, and it works across mothers that may not exist. So we created a polymorphic function that does this like useful thing of recovering an age. That's kind of cool. So functors, they might not be all that we need, right? So here is a really scary thing. I want to go down my mother's line, right? I want to get my mother's mother's mother. And we can do that. My mother's 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 age. And I can do that with successive maps. I get my mother, and then I map on my mother's mother, and then I map on my mother's mother's mother's, then I get the age out. And you can see what it does is it does this like option of option of option of int. That's not nice. So if I try and access that on me, right, I get a sum of a sum of a sum of 103. It worked. That's cool. We've managed to delve through multiple different values to get some value deep further up in my family tree. But if I try and get it on my mom, who doesn't have a great-grandmother, we get a sum of a none. That's effectively a none. We couldn't get it, right? Why is it telling us that it exists? It's saying that there's an existent value of an existent value of a non-existent value. So this is like semantically, like it's working, but it's just a bit dumb, right? We're doing these successive maps and we're getting nested values and we're getting values that it's like, it's there, it's not there. That's a bit weird. So it's working, but it's not what we want it to do, And here's like another one, it's called get all great grandparents' ages. And it works, kind of.
So you say that what you would like to get is either the number or none?
Yeah. So get all grandparents' ages, like get my parents, and then for each of my parents, I get their parents, and for each of my grandparents, I get their parents, and then I get their ages, right? We do a map, and we get them. We get 103 and we get 104. We get all these like intermediate lists in between. We're like, no, you just want a list, So we're seeing that every time we do a map, we get deeper in the layers of types. It's kind of cool. And here's one more example. This is where we're actually doing operations. We're not just delving deeper into the tree. We're going to go to two different places in the tree, and I'm going to do an operation. So here I try and get my mother. I get So remember how map works. So here I have an optional mother, like an optional family member. And then when we map, inside this lambda is a function that takes a family member. Did everyone get that? Cool. And then here inside that lambda, we nest it. We try and get our father. We have an optional father, and we map, we either get a father. And then here we add my age and my mother's age and my father's age, right? And so we get nested values. Just like for every map we did here, we get list, list, list. We have 2 maps here, so we get an option of an option in.
It feels like composition kind of thing.
Yeah, kind of. We're going to get there. A little bit. Not strictly. So here, sum of parents, we get a sum of 133. But if I try and do it on my mum, who we don't know about her dad, we get a sum of a none. So it didn't work. This sum worked, but this didn't work. We kind of wanted it to completely fail entirely. So we can hack our way out of this. We can have this function called flatten option that takes 2 options when they get nested and squishes them together. So if you have 2 sums inside of each other, it's kind of the same thing as a sum, you know? And if we have anything else, whether it's a none or it's a sum of a none, it's a none. It doesn't exist. We couldn't get to that value, right? And by hacking our way out of that, for every map time we call a respective flatten. And this works, you know? Here we try and get our great-grandmother, we get a sum of 103, that worked. And when I tried to get the great-grandmother of my mum, didn't work. Cool. So we're kind of there. So we're thinking, okay, we can flatten, for every map we do a flatten, and that would work with lists as well. And every time we do a map with a list, we do a flatten to get rid of all the nesting, right? So this is the crazy bit. That's a thing. That's the monad you keep hearing about. The monad you keep hearing about is something that is a type with flatten defined for it.
So for monads, the necessary bit is flatten function has to be defined.
Yeah.
And map, right?
Yes, because it's, funnily that, monads are also functors. So if you have map and you have flatten, you have a monad. That's all. That's all you need. So we're going to look at this, we're going to stare at this for a little while. So we say, for some monad, it has to be a functor, right? So when we create a monad, we also have to say the respective functor instance. We have this function called flatten, and it takes 2 layers of a monad and smushes them into 1 layer of a monad. Much the same way that this flatten option over here does that smush for us. Then we have flat map, which is a map and then a flatten, right? That's what we're doing here. Map and then flatten. Map then flatten, you know? So flat map is using the map defined by our functor and the flatten defined by our monad, right? The interesting thing is when you're defining a monad, you only have to define one or the other. Because we can define a flatten with a combination of a flat map and a function that does nothing for reasons that don't worry about it. And flat map is defined by just doing a map and then a flatten, right? And you can define one or the other, and then they will derive each other from each other, if that makes sense. They're kind of dependent in a weird kind of way. And then we have this other thing that you need for a monad called pure. And so pure takes some A and puts it in a monad. So, for example, pure for lists takes a value and puts it in a list. It's a list of 1.
Can you come again?
So I'll give an example. Do I have any examples down here? So for example, for lists, what we do is we take a value. Pure for a list is it just puts it in a list. A pure for an option just puts it in an option. All it does is it wraps it up. You know?
It's not identity function. Right?
It's not the identity function. It looks like it, and it does have some fun little interactions with the identity function, but it just pushes it into the monad, right? So part of monad is the ability to just it's like, it's the notion of putting it into a context. So we have a value, we want it to be a list, we go value.pure. It gets put into the list.
It's kind of just a constructor.
It's effectively, it calls the constructor for that type, it just puts it in. And we're going to see why that's kind of useful later on. So this is syntax bullshit that we've already seen. It's effectively boilerplate, for some A, we can call pure and it will give us that monad of A. If we have nested monads, it will call flatten on the instance for us. If we have monad normally, it will call flatten for us. So, it is boilerplate. We've seen all this syntax stuff before. So, not really that useful. Here's like some of the instances for the common types that we've seen before. So, for lists, pure just takes the value and puts it in a list. And then we're going to define flatten. A flatten for a list of lists is the flatten that is already defined on lists. This is really disgusting, mutability, like mutable code, because Scala doesn't really have a nice immutable implementation of how lists work. So we're just going to defer to the Scala standard library to explain how to do, how to flatten a list of lists. And flattening for our options is what we saw before. If it's a sum of sum, give us a sum. If it's neither of those, give us a none. Right? Cool. So we saw this ugly code before, and it worked, but it didn't work very well. Now it's going to work by just replacing those maps with flat maps. And so now you get a mother, flat map, and then finally a final map over here at the end to get our age at. And it gives us an unnested option. And as you can see, flat map, map, list of in. And here we have flat map and a map, right? So the general pattern is flat map, flat map, flat map, map. Flat map, flat map, flat map, map, right? Because the reason that is, I'm feeling this might not be immediately apparent. Is everyone understanding what I'm meaning here? Cool. So yeah, for example, this mother, this function here takes a mother and returns takes a family member and returns a list of family members. And so when we flat map, we map over every single family member. Oh, sorry, parents. We map over every single family member in this list, and we take a function that takes each family member and produces a list of family members, and this flat map is squishing them together at each layer.
So like that, doing the map is the last step. You could do that inside the last flat map, right?
Yes, you could actually.
So it's just nicer to not have it nested.
Yes. Now, that is correct. So one little interaction. Remember how I spoke to you, like what would you use pure for, right? So pure, for example, here, we could do this. Pure list, right? That would work, right? Because we're taking, now this is a function that takes a family member and returns a list of family members. With just those dimensions. Sorry?
List of hints.
A list of hints, sorry. Where the only thing in that list is the age we care about. And flat map works with that, right? So a flat map of a function composed with pure is the same as map. Because pure puts it, like, makes a new layer, and then flat map tears down a layer.
Sorry, can I ask a stupid question?
Yeah.
What would happen if you don't give pure of list in flat map?
It will freak out. It will say, oh, Jesus. Sorry, Bin is failing me with this latency. It will say flat map. Oh. It's once an iterable once, which is a list, that we've given it an int. So it wants us to give it a list.
So if you put the pure back,
Yep.
but then change the flat map to a map, you would get a list of lists of hints.
Yeah, you get a list of lists. You'll see, it will fuck up. Come on, type check. Oh, okay. So the reason why that is not working, because it's required int bound a list event. Because so that you have to make it a flat map, right?
So the right-hand side of last flat map is just a list with a single value in that.
Yeah, when we
Just
use pure.
pure, right?
Yeah.
Oh, okay.
So,
So obviously it makes sense.
So that's what pure does, is pushes it. And we can do exactly the same thing here. You know, we could go flat map and pure, right? Yeah, it's a duplicated code because it's general.
And we can also do something like list.add grandparents.age, right? Because it would return me a list in the end,
You could.
instead of using pure.
Yeah, you could do that. Cool. So this sum of age of parents that we saw from before, you know, now we use a flat map and then a map and it works. So you can kind of see all of that nesting is disappearing, right? Now, Scala has, funnily enough, Scala has nice syntax for this kind of stuff. Because you see these flat maps work because this is kind of like do one thing and then pass it to the next function. And then pass it to the next function. This is do one thing, pass it to the next function, pass it to the next function. But this one is a bit iffy because it's saying, get me my mother and get me my father. And we kind of start to nest function scopes. Can you see that? We've got two nested function scopes. If we wanted to add a third person, we'd have yet another flat map and it would keep getting deeper. And so you get this triangle of doom would start to be produced. So for notation, I'm showing you what is the literal desugaring. This desugars literally to this. Like it is a parser step in Scala. It will convert these arrows into that. So compare the two, stare at it, and then this is what Scala has the nice version of, right? And so we've seen promises with .then, and you've seen a sync await syntax. These are the awaits. Oh, fuck. That's cool, dude. These are like, each of those arrows is kind of like an await, right? For any monad, you know? Because it turns this into this, as you can see. Can you see what's going on? I think this is probably the better example. I'm actually just going to put them immediately underneath each other. You can kind of see what it's doing is it's taking, it goes, flat map binds this function, you know. So this binds this is effectively, it's producing a function here, right? This father produces, it binds a parameter here, this binds a parameter here, and then it yields, and that yield is that final map. So, yes, that is a literal transcription, it's a literal desugaring. And you'll kind of see something quite interesting is later on, I won't work for these, but yeah. Cool. Everyone make sense of that? Cool. So that's what happens when you go to Atlassian account, you see all these weird arrows. These weird arrows are turning into flat maps, you know, and they're turning into maps as well. So that's like what's going on here, you know? Cool. So I mentioned this is kind of similar to promises. Let's make a shitty promise type. I'm going to call it sync because it's not going to be async. It's going to be synchronous. But it's going to look like, you know, it's kind of look like a promise, right? So this is kind of spooky because it's going to do something a little weird. And there's some new syntax here. So we have this class sync of A, right? And it has a single value in its constructor called unsafe interpret. What it does is it takes a function that takes no parameters and gives us some A, right? So we could construct a sync of int by giving it a function that gives us an int, right? Gives us 5, right? That's a sync of int. We're allowed to do that. Ugh. New. Right? Sweet. That's allowed. Cool. Now we have this next function called effect, defined on the companion. It's effectively a static attribute. What it does is it takes a lazy value of A. I'm going to get to what that is. What it does is it takes that lazy value of A, wraps it in a function, and then constructs a sink. What I say lazy is that when we give that value to this function, it will not evaluate it. And even before it is evaluated, it will try and wrap it up in a function, right? So what that means, for example, ignore this bit, don't look. This function, when we call putStringLine with some string, it will not print it. That is a funny little weird bit about how Scala works. So I can call this function and it will not print anything. Because what it is doing is this function is taking a lazy A, which is this print line, and it will try and wrap it up in a function as soon as possible. That's kind of interesting, you know? That's kind of weird. So what we do is going to melt some brains. If you've understood so far, good. We're going to get into some like real hairy territory, right? So what we're seeing here is for a functor of one of these synchronous things, right? We have some sync of A, we have a function that takes some A to a B, and we want a sync of B, right? We've seen this before. We've seen an option of A, an A to a B, and an option of B. We've seen a list of A, an A to a B, and a list of B, right? Now we're going to do it with one of these promisey things, right? What we're going to do is we're going to take that sync of A, we're going to run the actual effect to get the A out. Then we're going to map over it. We're going to apply that function to the value that we've got out of it. And I'm going to wrap it up again. And the effect of wrapping it up again means that it didn't actually execute it. We've made a new value that says, when you execute it, you're going to get your old value out, then apply the function, and then wrap it again. So what we're doing is we're building a value that on successive maps constantly defers its computations. It's kind of hard to understand, but I hope everyone's getting it, right? So it means that we can call functions on things that don't run. It's kind of cool, you know? Did everyone get that? Okay. I don't think everyone got that. Anyway, so let's do a little bit. Like, oh Jesus, sorry. Let's do this. So we're going to go val putStringLine. X. Actually, we're going to go get string line. And we're going to call it. What are you upset about? Oh, it doesn't take pronouns, right? X map. X plus. Wait, gets a string. I'm just going to follow. Right. Oh, Jesus. Right. Oh, actually, that's not going to work. Don't worry. All good. Sorry, the brief interlude. Okay, cool. So here's so that's functor. We're mapping over something that doesn't exist yet. And so this is now the monad instance, right? So remember how we showed before we had fun? Say you have a sink inside a sink. It's some computation that hasn't run yet, contained inside a computation that hasn't run yet. Yep.
I have a question.
Yeah.
More Scala related.
Yeah.
The functor instance.
Yep. Why
Do
do
you need to define that there? Like, isn't the IO functor instance
right
implicit?
above? Yes.
Like, would Scala grab that since it's the implicit in scope and put it into that monad instance?
You could do that, but for various reasons we don't want to do that.
Would it work?
It would work, but it's better to explicitly say this monad extends this functor instance, because there's examples where some monad can depend on two different functors, and we want to disambiguate that, right? So yeah, here we have this. So pure is quite simple. it takes some value and it suspends it. It doesn't, wraps it in this lazy kind of thing. And then we have this computation inside a computation. And we want it to just be a computation array, right? So to do that, what we do is we run it, and then we run the next value inside of it, and then we suspend it again, right? We're explaining this is how you go from a lazy value to a lazy value of A, right? Lazy value of a lazy value of A to a lazy value of A, right? So here's what I showed you before. This put string line, right? It takes a thing, takes some sort of string, prints it, but suspends that operation. This, what it does is it reads from standard in, like it's a blocking operation, but suspends it. And then what we do is we create this computation chain through a bunch of flat maps. So what we have is we have this function, puts a string, and then we flat map on the result, and we bind it to nothing, and then we run this new thing called getStringLine, and then we flat map it, and it takes, we go getStringLine dot flat map gives a function that takes a string and returns a sync, right? Because we remember what our flat maps did. Our flat maps takes a thing of A, in this situation it's a sync of A, and an A, and returns a sync of B, right? And so here we have a sync of A, we have a sync of A, in this case a sync of string, to a string returns a sync of unit, right? We're allowed to do that, right? So here's the cool bit. When we run this is defined. This actually calls put string line. This calls print line. You will notice something, which is it does not print that at all. It doesn't pop up, right? Because the constructor, this sync effect, does not evaluate print line. But when we call unsafe interpret, oh my God, compiled. You'll see what, oh yeah, actually I didn't see this. Yeah, so this whole thing is equivalent to put string line, flat map, to some dummy value, get string line, flat map, to a string of put string line. It's taken its sweet old time. There we are. Cool. So now it's echoed. Now I can be like, hello world, and then it prints it. Echoing hello world. Ignore that. Did that make sense? I think I did a bad job of explaining that.
So the flat map of sync is kind of like the then of the promise.
Effectively, it's the then of the promise. And so here we have a value of something that does a computation. If we comment it out, it won't run. We can wrap things that do side effects up in this kind of monad, because it's a monad, right? Cool. We all got that? Still have 20 minutes. I'm going to break some brains. This bit's fun. Okay, function composition. We learned that in high school, hopefully.
So, 1 second.
Yeah.
So first you explain the monads.
Yep.
And then this sync thing.
Yeah.
So how does sync, what's the whole story like? Where is this taking us to? Are these two things that go usually together, or are you explaining this thing to build something later?
So we want to build fake Atlassian account. The whole we have this big confluence of interacting things, and I want to show finally how Atlassian account brings them together. But there's 10 of them. This is one of them.
These are the building blocks of
These are
Atlassian
the
account,
building
but the different functional programming concepts that Atlassian account uses.
Yes.
All right. So what's the role of sync in all this?
So
It is just how functional programming pushes the effects to the
to the
edges?
to the edges, right? So the edge is that, right? We've made some sort of we've done all these side effects, but they didn't run, right?
Yeah.
So functions can return these and not actually do stuff,
Yeah.
their values. And you can imagine, right, because this is a value, we could give this to some sort of interpreter and it could take, after each single flat map, it could give it to a different thread. You know, this is kind of like, there's hints of asynchrony here. Obviously it is synchronous.
Yeah.
But you can kind of see that through these flat maps and stuff, we can build things that like promises that would run in like, say, an event loop, right? We're going to use this eventually because it's going to be used for free, but that is 2 talks away, unfortunately. But it's there eventually. Okay, cool. Function composition. So this is, you know, show int, takes an int, gives a string. Kind of simple, gets the integer, calls toString on it. Nice. Is big string. Takes a string, gives a boolean. The length of the string is bigger than 5. It says it's true. It's big string. Is big number, we convert the number to a string and we check, and then is big string, right? So, ignore that. Okay, you didn't see that. So, and then is, yeah, cool, sweet. So, you know, when we print that, print's true. Yeah, cool. Ah, shit, I've ruined the surprise. You're going to have to squint at this. This is going to be, is it too small, by the way? Make it
That's all right.
Okay, cool. You're going to have to, like, really look at this. Look into the void. I'm actually going to make it bigger. There we are.
Get rid of the project.
Yeah, cool. Remember how a functor was some f of a and a mapping from a to b and gave you an f of b? What's that? Hypothetically, that's a to b, right? That's a to b. That's b. What's f?
Aspect?
Function. That. Oh. That is our f.
Is it not underscore to a string or the last, the right part of it, the function?
So it's a, yeah, it's a function. That is into string. It's a function. F of A to B gives us an F of B, right?
So, and then is a map over functions.
Yes. And then is a map over functions. So everything we've seen so far is we've been mapping over data, right? Mapping over a list. We've mapped over an option. Functions are data. We can map over them. Why can't we map over functions, right? The only thing that we need is the types to line up. And here the types line up. You take an f of A, where that is the f, and you have an A to a B, and we turn an f of B, where that is the f as well, right?
So to be clear, the F is the int and the arrow?
Yes, the f is the int and the arrow.
You can fit the delete thing,
Sorry?
like at the bottom there's a trash can.
Oh. Yeah, whoops, didn't see that. So, that's funny. So, obviously there's like lots of different like functions. Like there's like a very large number of things that we can go from. Like we don't just have to go for int, right? So for some arbitrary function of thing to something else, like we call this function arrow, right? So function arrow of some arbitrary type R is the functor. So here this is specifically function arrow to int of string, where that's f of A. And then that could be a string for all we care. That could be a function arrow from a string Could be anything, right? That's where we get to here. This is the functor instance for the function arrow. This is a real brain fuck. And I'm not showing you this because I think it's like funny to break people's brains. We use this shit in Atlassian account. We actively use this. It's got a different name, it's called Kleisli. Kleisli is some other things as well. But you do have to know this if you ever want to understand some of the more obscure aspects of Atlassian account. Not immediately, but eventually. So, this question mark means, question mark is a funny, it's actually a macro. That what it says is, remember when we scroll back, let's scroll back, right? Functor monad option, right? Can you see how this option, it takes some extra type parameter, right? We have an option of int, option of string, option of blah. This is a functor of option. It takes one extra thing. When we go to functor of r to question mark, we are saying that there's some extra type parameter that can fill this slot. In much the same way, underscore is this for functions. Like we can go like underscore and that creates like a parameter that we can then immediately call. We can go like underscore, you saw back here, we have like underscore toString. That creates a function that takes an x and then returns x to string. This is a type function that takes a question mark and returns r to question mark. So, and then this is where we do the magic. Remember, f of a, a to b, f of b. And then mapping is the same as, it's just the initial function and then the next function. The implementation of this and then is effectively what we do is it takes some function and then the next function and constructs a function that goes r to a and then a function that goes a to b and constructs an a to b. So it's kind of bridging the gap over the top. And we do that by creating a new function that takes an r, feeds that r to this function to pop out an a, and then we get that a and pass it into here, and then we get a b, and then we return the b. That's how we make a function that composes functions, right? We're constructing a function. Like up here, you can see here, we unwrapped it, ran the f, and then rewrapped it. And this is effectively unwrapping it, run the f, and then rewrapping it. Cool. And we saw that back with case x. Yeah, unwrap, run the function, rewrap. So the same thing kind of going on in all different situations. And you can do it with functions as well. All right, this is going to melt some brains. Okay, so yeah, cool. Here's an example. Show int, map is big string. It works. We can map over functions. We're allowed to do that. How much time do I have? 10 minutes. Sweet. Awesome. Ready? Let's do it.
What's this called? Is this reader?
This is called the reader monad.
What, sorry?
Reader. Because we're gonna see why it's called the reader in a second. They're also monads. You can call and like flat map on functions as well. You're gonna see why. Pure. Our happy little pure. Pure is interesting. Takes some a, puts it in the monad. So a becomes some r to an a, whatever it is. And it's simple. It makes a function that tosses away its parameter and just returns that a. Boop. Yeah, makes a function, and then when you call a function, you get that a out. Tell me if you don't understand anything here, because this takes like weeks We're going really fast here.
Can we just replace that R with an underscore?
Yep.
Oh, that,
Can do that.
With is big number.
Yeah.
Can you rewrite that using a lambda instead of is big string?
Um,
Okay.
I have to do that. Cool. I'll leave it like that if that makes more sense. Cool. So, Batman.
just quickly on that pure, that
Yeah.
particular thing, what's that called again? Is that A to B to A?
Pure.
Yeah, that implementation.
This one here or this one here?
On the pure,
Yeah.
you're going A to B to A, right?
A to B to A. Not sure I understand.
All right. We'll talk about afterwards.
Yeah, so it's taking a value A, returning an f of A,
Yeah, okay.
where that is the f, and there's the A inside of it.
Right, okay, sorry. Yeah, I misunderstood.
Flatten. So before we've done flatten before. Flatten doesn't really, like we can do flatten, like for functions, but it's really confusing. Doesn't really make sense, because you're trying to think of like, what's a nested function? It's an R to an R to an A. Like, how do I get in that situation? Brain breaks, right? So flat map. We saw before f of A to an A, f of A, where f is a monad, to an A, fuck it, let's actually just go to the implementation. Here we are. F of A and a function from A to an f of B to an f of B. That was flat map. Here we are. Oh. F of A to an f of B, f of B. And so what we do is we create this outer R here. We get that R. We feed it, we unwrap this to get the A by feeding the R. Now we have an A. Get the A, we feed it into that F, which gives us our R to B. Then we feed in the R again, and then that spits out an R to B. Because that's the B, and then here's our R to B. That's like really fucking confusing. Like, in fact, I'm actually going to do that. But that is unfortunately the most simple implementation I can give you. Doesn't get any clearer than that. Cool.
When would you use that?
We're going to look at that. We're going to do that.
It calls the first function.
Yep.
And then whatever that function returns, it calls the second function with, right?
Yep.
And that second function returns another function, which we just feed R into to unwrap.
Okay, correct. So, question. Here is our function takes in x plus 1.
Does it, my interpretation would be like kind of partial functions, like chain together.
A little bit. It's not quite chaining. Composition is like chaining, right? So we've got a thing and then this thing, right? The value goes in, comes out the other side, and we put it into the next function.
Yeah.
We're going to see what this flat map does, because it does something a little different. Does anyone want to guess what that does? Just by staring at the implementation, because it's a little spooky. So, we're just live coding here a bit. X plus 1. Like that. Come on, X, Y. This is going to be X. It's going to be actually X is Y plus 1. Yeah, fuck it. I don't want to do that. Okay. What happens is when we call flat maps, it makes it read from this parameter. So what's happening is when we're going, that's the f. So this is an f of a, right? That whole thing's an f of a. It's it's an int to an int, right? So what happens is when we call flat map on it, as you can see, it takes this r and it feeds it through to this next r as well. The same r is getting passed in to both points. That function there, and then that function there. So there's that a, and there's that this f of a takes an r. This f of b takes an r. Right. So what's happening is this r is getting threaded into every function. Right. And what you see is when we flat them together. Oh, so this is effectively. Oh, fuck! I keep forgetting that I've wrote these in advance. I'm like, man, I should have written this, but I didn't. So what's happening here is we have an x of int, and we flat map, and here we have a x of int, and we have two string, and then we have an x of int, and then we do an is even check, and then we take the is even check, and we tuple them all up again. As you can see, we've nested them in this kind of like weird diamond, right? And so what we do is then this whole thing turns into a function.
So it's just kind of, it's not composing the functions, it's just kind of like spreading out. Like you have one function that calls these other functions.
Yes.
And returns a tuple of the results.
Because we've returned a tuple.
Yeah.
It doesn't necessarily have to, but
Yeah. It
return whatever. So, yeah.
Wait, so in that add one, is that x plus one, or is that a function that returns x plus one?
This is a function, yeah. So this is a f of int. It's a function arrow from int to int. So it's a reader of int, and then this here, this is a function that takes an int and returns a function that takes an int and returns a string. And then this one is a function that takes a string and returns a function that returns a boolean. Oh, returns a function that takes an int that returns a boolean. And then this is our final function that takes a boolean and returns a tuple of that stuff. Right? And so this flat map implementation is, it's taking this, this, in the first example, it's taking our int to int, and it's taking our, as you can see here, our int to string, and returns our int to string. So it's reading from this int, right? Now, you're looking at this and you're thinking, that's incredibly stupid, because that's really hard to understand, right? And in reality, a lot of these monads, the people who work with them, functional programmers, don't know how it's working under the hood. All that they know is that when they do this, they can pass it in and all these functions will see it, We're starting to think of like, we have these monad implementations that we don't care about how they work under the hood. The only abstraction we care about is that when we do for notation, it works. But you can kind of see what the core lesson of this is. Functions themselves are monads, and then when we use functions in for notation, that the function, domain, right? It sees the domain of the parent function, effectively, right? That value gets passed down to everything, and they all return. We can bind the return value of this function. We can bind the return value of this function, and then bind the return value of this function. Sweet. That is the end of today's lesson. Any questions? It's a bit of a brain melt.
Do you have a concrete example of when something like this might be useful?
Yes, but it's with Clydesdale. If you want, we can do a real quick example of Clydesdale.
Could you just like explain in what situation this would be useful?
So, I'm going to scroll past the implementation, but it's going to be spooky. Screen internally. Here we go. Cool. You're going to see something a little interesting here. Read this as a function from a HTTP request to an option of an HTTP response. This one takes the HTTP request and checks whether it's a post. This one takes the HTTP request and checks whether it has an authorization header. This one takes the HTTP request and checks whether it has an object. As you can see, here is us reading from the HTTP request and returning body, and then we return response. Effectively what ACA directives do.
So it's what that ampersand does.
Yeah. But like this, well, we do it like this, right? And you can see here it is in practice. Yeah, when we pass in the post, it says, yep, sweet, I love that. But when we pass in get, it yells at us. It errors out. Doesn't return a result. You know, it didn't match on the route. The reason why Clydesdale is interesting, and we'll get to that later, is you'll notice something interesting is, what is interesting about this, by the way? Can anyone see it? Apart from the weird word, like, what do you notice that this is doing? This is a hint.
Error handling?
Sorry?
Error handling?
Yes. But what is it also doing? Reading from that request. Right? It's simultaneously, like if this extract body, if this post failed, as you can see here, so this post takes a request. If the post exists, it says some, it was there. Otherwise, nah, didn't find it. This one, looks into the parameter map, as you can see here, up here. That's the implementation of HTTP request. Looks inside the parameter map. If it can find it, it says, yeah, it's cool, sweet, here's the header. Otherwise, no, If one of these fails, this post request, the whole thing turns to none. We saw that before, right, with the option chains. Like, we tried to get our grandmother, couldn't find it, went to none, but if we could find it, we got a sum. And then, at the same time, it's reading from this HTTP request. So the flat map's doing two things. It's doing the option stuff, whether it's there or not, and then if it sees a none, it stops and ports the whole thing, goes to a none. And it's also reading from the HTTP request at exactly the same time. So there's this idea that we could get to later, but we can't do tonight, that we can do both. We can do two monads at once. Kind of cool. We can do reader, we can do the reader monad, which is the function, and we can do the option monad, which is kind of like exists, non-exist handle. And the really interesting bit is there's other monads that we can stack on top of each other. But we'll get to that later. So this is a glimpse of something greater to come. Cool.
Just out of curiosity, we
Yeah.
could have used either, right? Instead
Sorry?
of option, because either is better suited for error handling.
Yes.
Based on last discussion, yeah.
Yes, so either has the error message instead of the none. You have your right if it was yes, and you have left, which would be the error message. I can't find it. So that's also another monad, right? This could be a Clydesdale of either string, maybe.
Say, for example, that second step, the extract header.
Yeah.
Could you use the result of that in that third step?
Yeah. Or header. type checks. Come on.
So yeah, I have a, the other day I happened to see a video where they do the opposite. Instead of explaining how it works, they first explain what they want to get.
Yeah.
Which is actually the answer to your question. I can send you the video because I didn't know anything of this and now I'm disconnected.
Yeah. I tried to be like, this is what we want. We're going to get there next time. But like, as you can see here, that auth header is a string. You know, it's returned an optional string.
Okay, so that third step is only going to run at the second step as option, so the third step can use that auth header. Okay.
That's kind of cool. You know, we can chain these kind of operations.
So what's the role of types in all these, and how would it be, like, how different would it be, like, without types?
So in the next talk I give, I implement Kleist. The Kleist implementation. I'm just going to show you. It's very, very spooky. That Kleist R, FFA, run R, flatmap, run R, right? That's brain melting.
What, sorry?
Like that. That's really confusing, right? I couldn't write that because, like, I wrote that because the type system was just like, you got to do it. Like, I'd hit dot and it would be like, here's your dex type. And I used map by accident and it didn't work. It said you have to use flat map. I'm like, oh, sweet, right? So a lot of these really hairy implementations that, you know, you saw how immensely confusing that that flat, where was it? That was? Like, that's a bit brain melting, right?
Yeah.
That is the type system making you write that. Like,
So you're saying that type system is helping you
Yeah.
to get that?
Yeah.
But my question is, how much of that you have to do it because you have
Oh.
types? So you would have to do the same exactly.
very little. Like, like, if anything, like Scala is like liberating in that I can do this at all. Like, I've tried to do this in TypeScript. Nope. Like, I've tried to do it in,
Because it's too difficult.
yeah, it's too difficult. I've seen people try and do it in C#. Nope. Seen people try and do it in C++. Kind of there, but really, really, really terrifying. Like, this is,
But all these languages that you mentioned
Yeah.
have types. Right?
well, yeah, they do, but they're not as, you know, freeing as the Scala type.
So what I was wondering is if you can get away without doing some of that and getting the same result in a
In a dynamic language, yeah.
like-
So, the thing we kind of looked at in the first talk is that, if you go
Or
up,
yeah, not even dynamic, but like a less strict.
yeah, well, a strict one.
Strictly type.
So, like, part of the Scala type system is it needs to resolve, like, you can use, for example, this is like the implicit function, right? By specifying a type parameter, we can recover some t, right? So this is implicit value of a Boolean. This is implicit integer. By saying we want an implicit of a Boolean, it will recover that value. It will, like, literally scoop it up and cram it in to that function. And we can actually see that here. Oh shit, right? Show implicit hints. This is something I wanted to show people last time. You'll kind of very quickly see. Come on, give me my implicits. Yeah, cool. You can see here, it's when we call this function, it implicitly gets the implicit Boolean. Here we have this function is implicitly getting the implicit in, right? And so the core part of Scala, so we can give it a t and we can recover some sort of t with this function. This is like Scala's like entire like selling point. Like this is like 20 years of TLT research in one line, you know. Like we can say we have a list of int, we have an option of int. For some f, we can recover. Like we can say, you know,
That's basically implicit, right? Like,
Sorry?
you're saying you're talking about the Scala implicit.
yeah. So like, yeah, here we can,
Reference to like other times.
yeah, we can get the list of int and we can get the option of int, right? So because Scala can recover in type class instances, like it can recover an instance because it can ask for a higher kind three languages, to my knowledge, can do that in mainstream use. But Camel, Scala, and Haskell, no other language. And that is that entire these lines, that line here, right there, drives everything in this talk. Couldn't be done without it. Like, you try and write this code in any other language and it won't work. Bar Haskell. So, yes. Sweet. Oh, brilliant. Thank you for all for coming. Hope it was educational. Sorry for there were a bit at times I was actually brief interlude. We can kind of see how this works. You know, you can kind of see here that this f, because there's functor in it, we wrap it in the functor extensions implicit class that provides the .map function on it. How do you go back? Jesus. And then we can see here that it is recovering this functor instance defined here. So that you can, these implicit hints, particularly in IntelliJ, show you where all that data is getting threaded in to all these functions implicitly. And yeah, it's kind of cool to see, you know, it's pretty useful. It's quite a useful feature. Yeah, and you can see here, for example, sync, you can see that it's recovering the monad extensions that provides our flat map, and it's also recovering the monad instance so that our flat maps actually work.
So could you not do that with, say, just extension functions in colon?
No. You can't abstract over the extension functions. I could be proven wrong, but I don't think you can. Yes, that is particularly interesting because it is a syntactical transform from for notation. These are like, can I use a dot flat map function on something? If it can use a dot, like you can see here, this arrow here is actually the flat map defined against the monad extensions. It's kind of cool. Sweet. We're done. Politely next time. And state. State's fun. You'll love state. It allows us to do, you know, we can do stateful computations without any variables. Woo!
So how much of this you need to really understand in depth to like do just your daily work?
To contribute? No.
Actually, probably up to this point.
Like
Yeah.
I mean, I guess to write code probably not like nothing.
Yeah.
But I guess like to debug things or solve problems. Do you ever have to understand this?
Till the,
Do you want me to give my input on that?
yeah.
Because I had to learn this from scratch. I think Max has come into it knowing quite a lot. It's pretty quite interesting from mine and Peter's perspective. But I reckon up until this point where you understand that full comprehension.
You did?
Yeah, no, so yeah, up until the point where you start to understand how full comprehension works and start to be able to use that in practice, that's when you can start to contribute quite a lot. The Kleisli stuff, that's probably where I don't fully understand it. Yeah, I can still contribute to a lesson account quite actively, right?
Yeah.
So-
But anyway, like, could you? So my question is, what can you do if you don't know this?
What can't you do? You can't.
I think one
That's quite
example,
hard to answer.
for example, Mitch added tracing to the code base.
Yes.
And what he did is he modified the free monad destination type, and he turned that from just a simple future into a Kleisli. A Kleisli. So those are two things that we haven't looked at yet. To add tracing, right? So first of all, you need to understand how free monad does stuff and interprets things. And then you have to also know what is a Kleisli doing? Because if you can understand how a Kleisli works, you can understand how the tracing system
To be
works.
quite frank, I don't understand that.
So that change specifically required kind of, I wouldn't say deep knowledge, but like sufficient knowledge to understand that, like both of those things, you know? Because of that, another thing we looked at, you know, you saw this idea of Kleisli, right? We're mixing two monads together. We're mixing option and reader, the same time, right? We have in our type in Atlassian account a thing called an either future. It's effectively a sync and an either smushed together. To understand how to throw errors in that paradigm, you have to, that's the same, Jordan Chow had a big issue with it because he's like, how do I throw errors, right? You had to understand that these things were smushed together. And so that's what I want to do in a future talk is like, okay, cool. How do we smush monads together? You know? And once you understand that smushing, you start to understand more of an Atlassian account, right?
How is it different from like this Kleisli? How is that different from, or how is a Kleisli different from like a monad of a monad?
It is a monad of a monad.
So but like, could you just define like an option of a list of something, and that would, like, what advantage does it give you? Is it just nicer functions?
So, for example, you had X, right? List of option of X. Sorry, sum 5, right? No, right? When we do normal, right, like normally with this list, we would expect to see every single value in this list. This X would be bound to sum of 5 and there would be bound to none. If we did something, if we used the option T transformer, the only value X would ever be bound to would be 5.
The option T there is a Kleisli.
It's an option, it's a monad transformer. Kleislis are a monad transformer, specifically the reader T a monad transformer.
Okay.
And option T is the option transformer. And it changes how monads inside of monads behave. So if I didn't put that, it would do a completely different thing. But the core part is now this X that is getting popped out. It's only being bound to 5, right? Because the behavior of options is to get that inner value inside the option. The behavior for lists is to get that inner value inside the lists. And the behavior of an option T, given a list of options, is to get the inner value inside the list and the option.
But if you map over that option T, you still have a list of options.
You can't map over the option T, funnily enough.
So you can only flat map over it.
Actually, no, you're correct. When you map over the option T, the thing that you get out of on the left-hand side of that function is a list of option.
Like, it'd still be an option.
Oh, no, sorry, I'm talking shit. It's a value. It's a single value. It's an int. So if you call dot map over this, over here, you'd get, that would be an int.
Yeah, but what would map return?
That would return a list of sum of 6.
Okay. Yeah. So if
A list of sum of 6 and none.
So what if you had a list of sum of 5, comma, sum of 1, comma, none? What happens?
List, sum of 6, sum
What
of
are
2,
there 3 elements?
none. It's mapping over every single list, element in the list, and then it's mapping over the options.
Okay.
You see what's happening?
so it's just doing map over like the inner types, but it only calls the map, the function you pass to map, if it's in, there's something in the list and that's something in the sum.
Yes.
Okay.
But you saw what happened there. We combined 2 monads.
Yeah.
It's kind of cool, right? So what do we have in Atlassian account? We have tracing, we have error handling, we have asynchrony. We've got 3 monads.
Do you have one for feature flag?
No. We don't. But we could actually.
Yeah, you could do that.
We could quite easily. That could be a thing you could do. So we have stuck at 3 different things. So we could put all our monads on top of each other, and then whenever we flat mapped, it would do everything for us. See what's happening here? That's what we're going to get to. So the interesting promise here is, we're seeing glimpses of it, that each monad does something different. Lists have multiple values, options do and don't exist. Up here, we're going to get to it here. State is state. We do use state in Atlassian account, funny enough. This is how we store a value that we want to increment or decrement or put things in and take things out, right? The core promise of the monad is because we can put multiple layers of them in top of each other. When we do operations on them, all the layers get handled for us. So yes, interesting.
So I'm actually interested in, like, I mean, all this is new to me, but I'm interested in learning functional programming basically. So mainly because I think that expands like, your understanding of programming and things like that.
Yeah.
But the second reason why I'm interested in this is like a little bit more the political discussion about like functional programming, yes or no.
Yeah.
And on the second point, I'm wondering, one of the promises of functional programming is that, or one of the statements is that you should make reasoning about your code easier.
Easier,
But if then you have to understand all these, then
Does it help?
I mean, it's like I'm promising to understand easier something you are used to, but so you can get there, you need to understand a bunch of complicated things.
Yeah.
So then isn't it like a bit like
Yeah.
To give you like maybe a parallel, like if you use like Spring framework and like things like that, so you kind of have to understand like how to do annotations and all that kind of stuff if you want to build like all these routes and that kind of stuff. If you want to go and change a small function, it's just a small part, but you can just go change that small function, and you kind of know that the rest of the bloatware around it will deal with it. You can kind of achieve that with this stuff. You can go change a very small part of it and get away with it, and therefore do your day job, right? If you really want to start going out, oh, I want to create a route, or I want to, build this new controller stack, you have to kind of understand the framework and stuff around it. That's kind of similar with this. You have to understand that, for a controller to flow into a service, to flow into a database in the traditional free tiered architecture, whatever, you can do that stuff with this, but you can also do this in a well-known framework of any type. So if you're talking about the political aspect of, you have to know some like ground knowledge to do some deep stuff, that's true for anything.
Yeah.
It's just that it just so happens that in the industry there's so much focus on frameworks and OO languages, that's starting to change. Right? So you can see lots of like languages like Java and Kotlin are trying to do it, and some various others are bringing these functional concepts as first-class citizens. So therefore it's more likely that over time, Spring 5, for example, has to use annotations. You can use pattern matching on routes, right? That's exactly like it does in Scala.
Yeah.
So those features are starting to come through. So learning this stuff now is going to be valuable. The political aspect is going to change over time.
Yeah.
So
Yeah.
that's a question for you, whether you want to invest in it, right?
No, absolutely. I mean, I'm definitely interested in that because, like, regardless of how much you end up using it, I think it's a good learning. But I'm still. I mean, I guess I will find out myself the more, as I use it more. But even though I understand that anytime you need to do anything advanced in technology, you need to know the details. Still, my intuition is that understanding this well is fundamentally more difficult than understanding a framework well because of the nature of things. And actually, I can give you the example, like, there are much fewer mathematicians in the world than, I don't know, like other simpler, like the more you get into mathematics and pure mathematics, the more difficult it is and the fewer people there is. So I think this stuff is closer to that end.
Yeah.
And therefore it will be more difficult to grasp by most of people. I'm still unclear, I'm just like speaking out of my mind.
So I want to make a very quick disclaimer with like what I'm showing you is it's almost like a speed run of Atlassian account. It's a speed run of Atlassian account. It's like kind of like a grand tour.
Yeah, absolutely, I understand this.
Yeah, and there's things that I like. It isn't the best functional programming education, and if anything, some of the stuff that I will probably be teaching in the next talk, I don't personally think is the greatest thing to do, but is what we do. Yeah. That like, yeah, I think that's like kind of like important to realize like why the way we're approaching this kind of stuff. It's like it's not a very primitive look of functional programming. It's like almost like how do we bend Scala to do things that we want. Like we want it to look like this, and what can we do to get to that point? It's not like starting from the line of calculus. Now, a little thing I want to talk about is like, you're like, well, what's the kind of promise of functional programming? And I think this is my favorite snippet of Scala I've ever seen in my life. I think this is the core promise of, this is taking a Scala queue and in 30 lines, making it back pressured and thread safe. Like, it's now a concurrent queue, and that's it. That's That's all you did. That's all you needed. That's mind-blowing stuff. And the way is it's doing it with what's called a T-ref, which is a monad. It's doing it with software transactional memory, which is a monad. And it does this bunch of it does some applicative operation, and it's doing all this kind of spooky stuff that we're kind of seeing a little bits of it in like what we're learning, right? But it gives you the power to just make stuff like this, like express these really complex behavior. Just cool, because STM that does software transactional memory. It does this kind of asynchronous modification of values, right? And this monad does all of it for us, right? That we've taken all that complex stuff and put it in the monad. We've taken this reference type, this monad. We've taken all of the complexity and we've put it inside of that, right? And so we're now taking all these independent data types that do all the complex stuff for us, and then we're taking them and we're combining them. And this idea of the complexity is contained within the data and then functions. Like we only have a few core data types. We have our eaters, we have our, options, we have our lists, we have our STMs, we have our syncs and asyncs and IOs and stuff like that. That's all we need. And we have all these like hundreds of different functions that operate on them that are generic across a wide variety of different types, functors, monads, applicatives, whatever the hell we are. And with that, we have all this power contained in those data types. And it means that those data types are the Swiss Army knife for any problem we want. That is the promise. I think that is the promise of functional programming. And I think this is like the best example I've seen ever,
I think to add to that and add to your question, right, it's talking about, okay, it's quite a lot of stuff you have to learn. So is that actually making it simpler? So like an example would be throwing the word abstraction out, right? You're talking at a high abstraction level. So if you say like, oh yeah, lists and sets, right? We all know we can iterate over them. That simple concept to think that I can iterate over either a list or a set, that's quite simple to understand from a point of view, right? This is kind of taking that and going higher levels with it, right? And saying, if I understand these basic patterns that I see all over the place, and I can think of it at this abstraction level, and therefore it's simple. I don't have to reason about every single integral detail within that stack. So that's why some people, you start saying, oh, do I have to understand this to make it simple? Well, it really depends on what abstraction level you're looking for. And the power this gives you is a few more levels above. Yeah.
No, I mean, I get that. But I'm still, so what I'm still to see is, so, I mean, that statement would break as soon as sometimes you need to really understand it in depth. So if you could just always use the structure, that would be fine. But as soon as part of your job, regardless of how small it is, basically means that you need to get into that.
But you can. You could look into the implementation.
Yeah.
But fundamentally, you don't all, like, when you write code and you actually say Java or whatever, and you could say, oh, you use the interfaces, don't use the concrete types. You only care about like the base abstraction on top, right? You can always go through and look at the implementation detail if you need to. But generally, you just care about the type behavior and you can work out what's going to happen. This is taking that and then boom, boom, right?
This is a decent example.
Which is quite nice.
Like we have a state of integer, we can modify, we can put a value, we can modify it, add 1 to it, make that new value 10, subtract 2. That's like kind of a nice interface when you look at it, right? It's kind of simple, and then we say that we yield a string, the final value is 8, right? And we run it with an initial value 0. It kind of looks like a counter class, and then we just run these kind of operations against the value, But the implementation is utterly terrifying, right? But the only thing we care is that it's a monad, That's kind of like, yeah.
Therefore, it's simple.
It's simple, right? It's simple to us.
Right, you're looking at that level.
Yeah.
Thanks, Max. That's very useful.
Yeah, I mean, maybe I look like a little bit again.